Hi, everyone, and thank you for attending today's webinar, Deep Learning for Medical Imaging, Real-World Challenges and Opportunities. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A widget. We'll try to answer these questions during the webcast. Looks like we're ready to begin. Idan Bassuk will begin his presentation now.
Hello everyone. My name is Idan Bassuk. I'm the head of AI at Aidoc. And today we're going to talk about deep learning for medical imaging, how we use it here at Aidoc, the real-world challenges that we face at large scale, and the opportunities that the state-of-the-art technology enables us when facing these challenges. So I'm really glad to see all the people that registered for the talk and joined us. And first, I want to start with a few words about us, about Aidoc. So we are the leader in AI for radiologists. We offer a comprehensive suite of AI solutions that are always on. They are running constantly in the background, analyzing each and every scan. And our solutions that analyze every scan help radiologists identify critical findings in these scans and thus optimize their workflow. And I want to just mention a few achievements of our company. So first of all, we are FDA and CE cleared. We are serving over 60 medical centers worldwide, especially in the United States and Europe. Many of them among the top medical centers in the world. We have recently passed our 1 millionth analyzed scan in production. And not only that, we are very happy to see that we are seeing very high levels of user engagement. But we are even trying to do more than that. We are very focused on proving the medical and the clinical value that our product, that our solutions are giving to customers in real clinical settings. And in order to do that, we are cooperating with some of the medical centers that we are serving in writing 11 academic publications. And our goal in these publications is to demonstrate with high level of confidence and over a very large data from the real-life setting to demonstrate and to prove the real clinical value that our solutions are giving. Okay, so let's begin. I want to start by stating the outline of this talk. The first part will talk about the challenges that are relatively unique to medical imaging in computer vision. In the second part, I'll talk about how we can solve some of these challenges very elegantly using state-of-the-art deep learning. In the third part, I'll talk about how to move from algorithm to a solution that gives real clinical value. And in the last part, we'll summarize and answer some questions. So the first three parts will be about 40 minutes from now. So let's start with the challenges of the computer vision challenges that we face with medical imaging data. And the first challenge I want to talk about is the extreme class imbalance. And what do I mean by class imbalance? By class imbalance, I mean that the targets, the findings that our algorithms are aiming to detect are very, very small compared to the image and compared to the data set. And they are very, very rare in the data. As an example, you can see two images in this slide. In the right image, you can see a single slice from a 3D brain CT scan. and the arrow in the right image is an arrow generated by our product and by our algorithm that is pointing on a very, very small and subtle hemorrhage in the brain. By the way, this hemorrhage exactly was missed by a radiologist. And just to demonstrate how subtle and small this hemorrhage is, you can see on the left a zoomed-in image on the same slice, and you can see that the hemorrhage, for those of you that are non-radiologists, is the very small, bright spot that the arrow is pointing on. And you can see that even when you look at this slice only, which has about 1 million pixels, the size of the hemorrhage compared to the size of the slice is a very, very tiny fraction. But not only that, a single image in radiology is a 3D image. So actually you can think, when you think about it, the few pixels of this hemorrhage should be counted not out of the single slice, but they should be counted out of the entire 3D scan, which contains sometimes almost a billion pixels, tens and hundreds of millions of pixels. So the targets are very small compared to the data, and not only that, most of the data is of healthy people, not of people that have hemorrhages or fractures, which makes the target even more rare compared to the number of pixels in the data set. And just to compare that to the classical challenge in a classical computer vision data set, I put on the left an image that is like a typical image from a pedestrian detection data set, which could maybe be used by an autonomous vehicle algorithm. And in this case, the findings that this algorithm will try to detect are the people in the image. You can see that the number of pixels of these people, of the number of pixels that belong to the people in the image, divided by the total number of pixels in the image, the people are a much larger part of the image than the hemorrhage outside of the brain image, and without even, and that's even much more extreme when you remember that the CT is actually a 3D scan containing 100 different slices, of which the hemorrhage only appears in about 1 to 3. So this is the first challenge that I wanted to talk about, class imbalance. And the second challenge, which is very interesting also, is the challenge of the large 3D volumes. And first of all, you can see that from classical computer vision data sets that are being researched all over the academy and large companies, typical images of cats that are being used to train and test these algorithms are about 30 times smaller than the typical image in medical imaging. So the images are 30 times, the medical imaging images are 30 times larger, but the object size is 10 times smaller. So the challenge of the 3D volumes give us a lot of different challenges. Some of them are computational, some of them are algorithmic, and I want to focus on one very interesting challenge that we have solved in our company. And I want to demonstrate it using an example. And here you can see two slices of the same CT scan, the same 3D CT scan of the chest. And let's start by focusing on the left slice. So as I said, this is a slice from a chest CT scan. It's actually, for those of you who are radiologists or in the field, this is a CTPA scan. This is a scan which goal is to find PE, a finding called PE, which is pulmonary embolism. It's a very small finding inside the arteries of the lung. And in the left image, you can see the arrow generated by our product that is pointing at a very, very subtle PE finding inside an artery. And even more than that, it's important to mention that this specific scan is a relatively very challenging scan compared to the regular scan of that type, because these scans are acquired when using a contrast agent that is injected into the blood circulation, and in this scan, the contrast agent the scan was not acquired properly, so the contrast is very, very, very suboptimal, making the PE much harder to detect. So the PE is much harder to detect, and actually it was also missed by a radiologist in a hospital, and our algorithm was able to find it. So how were we able to solve this challenge? We did it by doing two things, among others, but I want to focus on two things. First of all, we had our algorithm we steered the attention of our algorithm to zoom in on the suspicious artery. So in the bottom left corner, you can see a zoomed in image of the artery that the algorithm suspected for containing PE. And as a secondary classification stage, we give the algorithm only this very zoomed in image in order to classify if it indeed contains PE or not. But this is not the only thing we do. One of the drawbacks of doing only that, especially in scans with suboptimal contrast, is that by looking at this zoomed in image, we have no way of knowing if this blood vessel is an artery or a vein. And if this is a vein, it's not a PE. The only way to know if this is an artery for sure is to track this blood vessel in the 3D volume, now you can look at the right image, and this is another slice from the same CT scan. And in the middle of the scan, in the middle of the slice, you can see a huge artery. This artery is the main pulmonary artery, the main artery of the lung. So the only way to make sure that the suspected artery on the left slice is indeed an artery, we need to track it down in the 3D volume and go and scroll through 20 slices until we reach the slice on the right and see that it intersects and originates inside this huge artery. So in order to do that, we had to develop a component that enables our algorithm to track the blood vessel through a large 3D volume. And so to recap, our algorithm does two things. First of all, it focuses on the smallest scale in the image, on the zoomed in image you can see in the bottom left corner, and it fuses its insights from this zoomed in image together with its insights that it's generated by tracking the artery through a large 3D volume. And only then it makes the final decision regarding the classification of the PE. So these were the first two challenges. Now I want to talk about the third challenge, which is the deformability. Targets in medical imaging are typically much more deformable. They don't have a regularized form and are much less rigid than typical targets for computer vision data sets and algorithms. So you can see the image on the left. How do I, as an intuition to what it means to have a deformable target, can see the image on the left, which can also be a classic image for a pedestrian detection algorithm. And you take your target, which, for example, is the person in the image, and you bound that person with a rectangle. From now on, I'll call these bounding rectangles, I'll call them bounding boxes. So when you bound the person with a rectangle, you can see that the person is a very large part of that bounding rectangle. In parallel, you can look at the medical image on the right, and the pixels that I colored in yellow, it's not their original color, I colored them to help you see it, are a very, very subtle brain hemorrhage. And when you bound this brain hemorrhage with a rectangle, with a bounding box, you see that the pixels of the hemorrhage are a very small part of that rectangle. So basically, the deformability, and one measure to quantify it is when you take your finding and bound it with a bounding box, how, if your finding is only a very small part of the bounding box, then your finding is probably very deformable. And you can see that, and it's very, very typical that medical imaging findings will be much more deformable than typical findings. So we covered 3 challenges so far. Just to recap, I'll remind you, we covered the class imbalance, the challenge of the large 3D volumes and attention in multiple scales, from the smallest zoomed-in scale to the largest 3D scale through dozens of CT slices. And we covered the challenge of the deformability of the findings. And the last challenge that I want to talk about in this overview, and then I'll go to the solutions, is the challenge of the data being polyglot. And for those of you who don't know this term, polyglot means multilingual. So when a radiologist diagnoses a CT scan, she doesn't only look at the image itself. The radiologists look at many, many other informations that they have about the scan and the patient. So the types of information that we have starts from the demographics of that patient, and we also have the referral letter from the referring physician that asks for that CT scan or MRI scan. We have other images which are the past scans. Maybe that patient had previous scans that he had underwent a year ago, or 5 years ago, or 10 years ago, or an hour ago, and we can take them all into consideration. And they really indeed can help us. And the reports, the textual, unstructured reports written by radiologists on these scans. And we also have the scanner metadata, which contains the information about the geometry of the scan and other types of information. So you can see that there are a lot of types of information. Some of them are structured. Most of them are completely unstructured. And not only that, they are completely unstandardized. Every CT technician or doctor, even inside the same hospital, and especially when you're trying to cover hundreds of hospitals, you're going to see a mess in your data. And it makes it even more challenging to be able to use and to utilize all of these types of data. The images are really standardized compared to all the rest of this patient data. So these were the challenges that I wanted to cover, and of course there are many, many more challenges, but I just wanted to give you a quick overview of some of the really main and most interesting challenges. And now I want to go over deep learning solutions, some solutions for these challenges that the state-of-the-art of deep learning enables us. But before I dive into the specific solutions, I want to talk about the overarching rationale for finding solutions in computer vision problems. So theoretically, the simplest neural network architecture can find the most optimal solutions. Theoretically, mathematically speaking, you don't need deep learning scientists. But practically, it doesn't work. Why doesn't it work? So for those of you who are knowledgeable regarding deep learning, the simplest architecture that I'm referring to is a shallow, fully connected network. If you're not knowledgeable in deep learning, it doesn't matter. So don't worry if you didn't understand that term. But I'll just explain what it means. This simplest architecture takes your image and takes all the pixel values, puts them in a very, very long list, and throws them into a calculation machine. What is the problem with this simplistic approach? Why mathematically it can solve any problem and give the most optimal solution, but practically it doesn't? The problem is TMI, too much information. We're giving the neural network too much information to make sense of, and there are many, many possible solutions. So inside all this mess, it can't, and inside all this information, it can't find its way efficiently to the most optimal solution, even though theoretically it can model it. So I'm stealing the traditional computer vision intuition in order to explain the overarching rationale for what we're doing here. A much better architecture than the simplistic architecture is CNN. So what does a CNN do better than the simplistic architecture from the previous slide? In a CNN, instead of taking all of the pixels, putting them in a list and throwing them into the calculation machine, we focus on a very small part of the image at each time. So in the left image in this slide, you can see a bright square. This square is a demonstration of what it means focusing on a very small part of the image. When we take only that small part of the image, and only that we throw into the calculation machine. And by doing that, we significantly reduced the amount of information that we are giving to the neural network. So when we gave a much more focused problem to the neural network, we are able to get a much better answer. And even though it's a simple answer, it's still an answer that we can do something with. So the answer that the neural network gives us when we narrow down the amount of information that we give it is, hey, there's a line here. It identifies the edges of the person. And now that we have the edges, we can add on top of the edges additional layers that can find more and more abstract concepts out of these edges, for example. So this is an example of the overarching rationale, which means that by focusing and narrowing down the problem that your neural network should solve, you're increasing your chances of success drastically. So to say it in a very general sense, the essence of the design of neural network architectures is to steer the neural network to utilize the information in a very specific way and in a much more narrowed down way to simplify the problem that you're giving the neural network to solve, using considerations that only us as humans can understand what are the correct simplifications that we can give the neural network to solve. And if I take it into the world of medical imaging, we try to think how to apply this rationale in the world of medical imaging data. And what we saw from the very early days of our company is that even the state-of-the-art deep learning techniques that are proven on classical data sets don't work out of the box for many medical imaging problems. We take the state-of-the-art solutions that win the challenges in all computer vision competitions, and they don't even find a single hemorrhage when trained on brain scans. So we try to think what we are lacking here. And the solution was to generalize this rationale and to take it to the world of medical imaging. And our rationale is to steer the network to utilize the information in a more specific way. But the more specific way that we are aiming to is to utilize the information more like a radiologist. So our goal is to find how to design the architecture of the neural network that can possibly find an infinite number of solutions and narrow it down to only find the solutions in a much narrowed down search space. And this search space is defined by the way that a radiologist will look at the image. And now that we understand this rationale, I want to give a few examples. So this is the example that I already gave earlier about how we utilize both the most zoomed in scale and the largest 3D scale, tracking the artery through 20 3D slices. And this is this architecture for the algorithm was inspired by the way radiologists look at the data. So theoretically, we could have just taken the 3D images and thrown them into the CNN, and theoretically, certain types of CNNs would have been able to learn these type of solutions by themselves. But they can also learn a million other solutions. So the chance of converging into this specific solution is very small. But once we understood this is the way a radiologist looks at this image, we made an effort to design the architecture of the algorithm in order to focus the solutions that can be learned more to this type of solutions. And we were successful in doing that. And by doing so, we were able to find very subtle findings in scans that are suboptimal for this pathology that were missed by expert radiologists. And another challenge is the deformability of the targets. And I'm going to, and this is just a quick reminder of the less deformable target on the left from traditional computer vision data sets and the highly deformable target on the right from the medical imaging data sets. And I want to talk about a fascinating paper by Microsoft Research that gave a very nice solution that we used as the basis and took it and we adapted it to solve these kinds of problems in medical imaging. And this solution is called Deformable Convolutional Networks. And they published 2 papers on this subject. So as you can see, the problem of deformable objects does exist also in classic data sets. So here you can see an image of a cat. And you can see that if you look, ignore the red rectangles for now, just look at the large yellow rectangle that bounds the entire cat, you can see that most of the pixels inside the area of this rectangle are pixels of the floor or the wall, are not pixels of the cat. So what is the problem with that? I want to emphasize it. The problem is that when the neural network wants to take this rectangle and make a final decision about it, it gets confused. Because in many cases, it will get confused and think, okay, there is some essence of a cat here, but this is mostly a wall. So I'm just going to say it's a wall and not a cat. And the solution that Microsoft Research proposed is we have this bounding rectangle that the first stage of the algorithm gave us. And now before we make the final decision, before the algorithm makes the final decision, the final classification, we have a sub-algorithm, a sub-component of our neural network that takes this rectangle and generates 9 other rectangles. These are the 9 red rectangles. So we have a sub-component of our algorithm that generates 9 smaller rectangles inside the large rectangle. And the final decision stage of the algorithm will only utilize the data inside the smaller rectangles. So when you give the neural network when you steer the neural network to look at the problem this way, eventually the solutions that it learns are similar to what you see on the image. The smaller red rectangles track the cat very, very nicely. So if you look at the area under the small red rectangles, you can see that only a very, very small part of it is pixels of wall. And a much larger part of the information under these red rectangles is information about the cat, which increases the success probability of the neural network by a very large margin. And I want to show an additional example of it from a classical data set that was given in the same paper by Microsoft. And you can see again that the woman that is reaching her arm, standing her arm forward, you can see that the yellow large bounding box that bounds it contains mostly pixels of wall and of the fax machine, and the new component, the deformable component of our algorithm, takes this large rectangle and generates 9 smaller red rectangles that follow the structure of the woman much more closely, increasing the success probability of the network, of the algorithm, in a very large factor. And what is the value that it gives us on medical imaging? You can see the same example that I gave earlier of the highly deformable but typical brain hemorrhage and the yellow bounding boxes that bound it. And you can see that when you add the deformable subcomponents, we get nine smaller rectangles which track the pixels of the hemorrhage much more closely. So if the original yellow rectangle, many of the pixels there were healthy brain tissue. So if I would only take the pixels under the yellow rectangle and ask the algorithm to make the final decision, in many cases it will get confused because it will think, okay, there is some essence of a hemorrhage here, but there is mostly healthy brain tissue here. So to be on the safe side, I'm going to say this is healthy brain tissue. But when you use the deformable component that we took as inspiration from this paper and adapted to the medical imaging world, you can see that it tracks the hemorrhage much more closely. It enables the algorithm to simplify the problem in a much greater way. And if we want to recap it and connect it to the rationale that I talked about earlier, we can actually say that what this type of solution does is it steers the network's learning process to utilize mostly the foreground pixels of the suspected finding. And if you think about it, this is basically how a radiologist and how a human will look at this image. Because when a radiologist looks at this image, first of all, he's doing a very quick scan of the image and finds suspicious areas for hemorrhages. And even if it happens subconsciously, you can say, you can paraphrase it and say that he puts bounding boxes around these suspected areas. But when he zooms in order to investigate and make his final decision or her final decision about these suspected bounding boxes, it's completely clear to him that many of the pixels in this bounding box are not relevant for the decision because they are completely healthy brain tissue. So he only makes his decision based on the suspicious pixels inside that bounding box. So this type of solution, the reason that we liked it and we wanted to take inspiration from it is that we understood that it will help us build a neural network architecture in a way that it will narrow down the way that it works to work much more closely to how a radiologist works and try to imitate it much more closely. So unfortunately, I wanted to cover another paper, but we won't have time for it today. But if you want I have an online presentation of this paper from another conference. So if you want, in the email later, you will get my contact details from NVIDIA. and you'll be able to reach out to me in order to get this presentation, or you can just Google my name and try to find it on YouTube. So this solution was mainly what I wanted to say here is how we, one of the solutions that we use in order to help our neural network and our algorithms be able to detect very, very small and subtle findings, like this very small cervical spine fracture, or the hemorrhage that we saw earlier, or the PE that we also saw earlier. But as I said, we'll have to skip it for now, because we have another chapter of this presentation, which I think is very interesting and really important. So the chapter that I'm talking about is the real-world challenges and opportunities. And everything we talked about so far were also real-world challenges, but they were these were challenges in building an algorithm. But in order to be successful and in order to build the product and the solution that radiologists need, that the medical centers need, that the medical world needs, an algorithm is not enough. You need to build a product around this algorithm, and you need to build a holistic solution around this algorithm. And I'll explain what it means now. But basically, when people, especially when deep learning, it's a very young and it's a very academic field these days. And many of the papers and the material that gets published around medical imaging challenges and solutions focuses on the accuracy of these algorithms. The accuracy, the sensitivity, the specificity, the F-score, the area under curves, and all of these other metrics for the accuracy of these algorithms. But my claim is that accuracy is not enough, our claim as a company. So how do you move from algorithm to solution? First of all, to move from an algorithm to solution, so I'll combine it to several parts. And the first part is, in order to move from an algorithm to a solution, you need to focus on clinical outcomes. You need to ask yourself what really gives clinical value. And then you need to ask yourself, how do you measure yourself better in order to give this clinical value? Because as I said, sensitivity and specificity, high sensitivity and specificity of the algorithm, it's a necessary condition for good clinical outcome, but it's not sufficient to give clinical value. Because even if you have, for example, let's imagine as an example, okay, that we built a very, very, very accurate algorithm, but it takes 30 minutes to run. The clinical outcome of this algorithm is very low because for many pathologies, especially in acute situation and in trauma settings, because 30 minutes running time for the algorithm is not enough to be relevant for the radiologist in real time. So you need to focus on the clinical outcomes that your customers need, and not only on the metrics of your algorithm. The second part of moving from an algorithm to a solution is that building a single accurate algorithm is, to tell the truth, it's relatively easy. It's not very easy. As I said, it's not out of the box. You don't just take TensorFlow and Keras and run it on your medical imaging data. That won't work. But if you take good deep learning engineers and AI engineers, they will be able to build, it will be relatively easy for them to build a relatively accurate algorithm. But the real world, the medical world, doesn't need a single algorithm. The real world needs a comprehensive solution, a solution that can detect dozens and hundreds of medical pathologies. This is what we call a comprehensive suite of solutions and algorithms. So the real challenge, in our opinion, is building many algorithms, building a conveyor belt for algorithms, a factory. And in Aidoc, we build a conveyor belt that enables us to release a new algorithm that detects a new pathology in a new body part once in every month. And this is much more challenging than building a single algorithm, because reproducing your success month after month, the first algorithm took us 1.5 years to build. And now we're able to release a new algorithm to production every month. And this requires a highly coordinated effort between the most advanced research and very, very precise engineering. For example, I think one thing that many AI teams, not only in the radiology domain, get wrong is exactly in the field of good engineering. For example, they don't write tests for the infrastructure that builds this algorithm. So when you build your first algorithm, it works. But then you continue working with this infrastructure, and you introduce bugs into this infrastructure. And once you reach your fourth algorithm, you don't get good results. But you have no way of knowing if this problem originates in the data being hard, which means you need more research, or in many cases, your problem will originate in a bug, a software bug that you injected into your code by mistake. And if you don't have tests, and if you don't write your code in a very, very good way with the highest standards, you will not be able to build a conveyor belt for algorithms. And the third part of moving from an algorithm to a solution is scaling up in production. As I started with, we are aiming to build a solution that is always on, analyzing every scan in the background before the radiologist was able to read it himself or herself. And we want to do it for every hospital, every medical center worldwide. And in order to do that in hundreds and thousands and tens of thousands of medical centers, you need world-class engineering of your production platform with high availability and reliability. And it's very difficult, even if you do it for any case, but especially when you build such a highly available and reliable platform around dozens of different deep learning algorithms that need to run in real time and be able to adapt to the changing demands of hospitals and the peaks between, for example, peak times and low times. And another challenge for scaling up in production is something that I already mentioned a little bit, is that medical imaging data is a complete mess. There is no standardization between medical centers. And many of the fields inside medical imaging data, inside DICOM files, for those of you that know it, change because of typos that the technicians that acquire the CT scan make. So they even change between different technicians and between every technician to himself, because he made a typo once and made a different typo the other time. So this causes many challenges. But for example, just routing the relevant data to each algorithm in hundreds of medical centers, it's an algorithm and it's a system of its own. Okay, so this was a little bit more about the real-world challenges of moving from an algorithm to a solution. And in the next minute, I want to summarize and to recap, and then we'll have about 10-15 minutes for questions. So to summarize, medical imaging data poses several challenges to conventional deep learning techniques. And the overarching rationale for the solution remains the same. the overarching rationale, as we talked about it, is to steer the network, the algorithm, in order to utilize the information in specific ways that the deep learning engineers think are more appropriate in order to solve this type of problem. And in the case of medical imaging, the overarching rationale is to steer the network to utilize the information like a radiologist. And in order to be able to do that and to solve very complex problems, and we presented many of the challenges like the class imbalance and the deformability of the objects and the 3D nature of the images, etc., and the polyglot nature of the data, it's very important to always stay on the cutting edge of the research in AI in order to be able to leverage the latest advances. But since there are many, many, many advances all of the time, and some of them are more relevant, some of them are less relevant to medical imaging, you need a very strong AI team in order to prioritize. First of all, in order to be able to even keep up with the innovation in this field. And second, in order to prioritize the most important directions, because you will not have a time to try all directions. And not only that, even once you take a good direction and you prioritize it, in many cases, it will not work as is on the medical imaging data. You will need to adapt it to the medical imaging domain. But in parallel, I think that something that makes AI teams even stronger is the other side of being able to combine the most innovative, and I think that the strongest AI teams in the industry are the teams that are able to combine the knowledge and the capabilities in the cutting edge, but with keeping your feet on the ground and remembering that simplicity wins. If you can build a simple solution that will take 10% of your time, you don't need to waste your time on the latest paper that was published from the Ivy League universities. And the last part of the summary is that the most significant barrier to success, in my opinion, is there are very, very significant challenges in the algorithms, don't get me wrong. But I think that the most significant barrier to success, and this is what most companies, I think, will get wrong, is you need to build a solution, not only an algorithm. It's very easy to fall into this trap and think that the main problem here is the problem of building an algorithm that works. This is an easy problem relatively to building a solution that works. And in order to do that, you need to understand what are the clinical outcomes, be able to measure them in the real world setting, and be able to set the goals to your algorithm and to your software platform to reach and optimize these clinical outcomes. And you need to build not only a single accurate algorithm. This is easy. You need to build a comprehensive suite of dozens of algorithms. And the only way to do it with a small team is to build a conveyor belt for algorithms. And in order to do that, you need not only the best deep learning researchers, you need these deep learning researchers to be also the best software engineers and to write code with the highest standards and to write tests. And this is very rare in the deep learning community. And the third barrier for building a solution is to be able to scale it up in production to hundreds and thousands of medical centers while remaining always on, remaining available, reliable, and finding your way inside the mess of the unstandardized medical imaging data. Thank you very much, and I'd love to answer your questions now. Okay, so I'm going over the questions. Let me look at it for very quickly, and you're welcome to write more questions in the meanwhile. Just give me a minute to read through the questions and choose the questions that will be the most relevant to the audience. Okay, a very interesting question that I really relate to. Do you think AI will eventually replace radiologists? I don't think that will happen for several reasons. First of all, I want to say I don't think that will happen. Definitely not soon. Definitely not in the coming years, and even not in the coming decades. And for that reason, our company is not trying to replace the radiologist. Our company is trying to integrate seamlessly into the radiologist workflow and help her optimize her workflow and succeed more in the same workflow. And the algorithm has many advantages that make it a very good partner for the radiologist. For example, the algorithm never gets tired. So I don't think that AI will replace radiologists soon or in the foreseeable future. And one of the reasons for that is that today, huge parts of the world, for example, in the second and third world, almost don't have any radiologists that read the scans there, right? Even the scans that do get acquired barely get read and get read in a very untimely fashion because of the very small amount of radiologists in those areas, and the fact that these parts of the world don't have enough money to pay the radiologists, enough radiologists. So I think that as AI will become more, I think that, in my opinion, we will see two processes in parallel. On the one hand, one vector that we're going to see is CT scanners and MRI scanners are getting cheaper and cheaper, and will become cheaper and cheaper, or X-ray scanners will become cheaper to acquire a single scan. And in parallel, medical imaging will replace radiologists in certain aspects, but you will always need a radiologist to have some sort of oversight on the outputs of the AI. So as AI becomes more independent, the same amount of radiologists will be able to give service to a growing portion of the population of the world. This is the way that I see it. And I hope to see it, because I really hope that we will be able to improve the clinical outcomes, not only for the Western world, but also for developing countries. Let me see. Choose another question. So the question is, your point about algorithm and solutions is 100% on the money. Thank you. And the question is, seen from real production life and not academia, how far are you in clinical certification for your solution? So as I said, first of all, we are FDA and CE cleared, and we are already serving over 60 medical centers, and we are very confident in saying that we are giving tremendous value in these clinical centers, which include some of the top hospitals in the US and Europe. And we are able to help radiologists find patients that get missed on a daily basis. Let me choose the next question. So the next question is core presentation. Thanks again. Any references you can share on 3D attention? So unfortunately, I think that the solution that we developed here, it's a relatively unique solution, and as for now, we are not planning to publish it. We might decide to publish it in the future. So if you're interested in that, you might want to follow me, and NVIDIA will publish a PDF with my contact details as a follow-up email to this conversation. But unfortunately, I'm not able to share it, but you can follow us in order to maybe get references to things that we publish in the future. Next question, do you train on clusters? If so, what distributed learning tools do you use? So that's a great question. We do train on clusters, and by that I mean we train our neural networks on many GPUs in parallel and not only on a single GPU. And we even published a blog post about it. So if you go to our company's website and go to our company blog, you'll be able to find a blog post that we wrote about it. And we are using a framework developed by Uber that is called Horovod. Horovod is a framework that is based on the technology behind how to use Horovod is mainly centered around two papers. One paper is by Facebook. It's called Training ImageNet in 1 hour. And the second paper or solution is by Baidu, which popularized an algorithm called ring-all reduce. I don't want to go into the mathematical details about it, but you can get references to it from our blog post. But what I can say that Horovod works very well, and it helps us shorten our training times from days to hours, which was critical to our research velocity, and it was a critical component in our path to building a conveyor belt for algorithms. Okay, we have time for one last question. So unfortunately, there are many questions, and I won't be able to answer all of them now. So I'll just say that you can feel free to contact me on LinkedIn after this presentation. Send me a message, and I'll do my best to answer your question. It will probably take me several days even more than that, in order to get to all of your questions, but I will definitely love to do that. So let's see if there's a question that I can answer in the minute that we have remaining. Is your deep learning architecture trained end-to-end? Large parts of it, very large parts of it, are trained end-to-end. And for example, I think you can see a very fascinating example of end-to-end training in Microsoft's papers about the deformable convolutional networks, which they have shown to be able to learn end-to-end. But as I said, I think one of the virtues of strong AI teams is to be able to find simple solutions. And many times, finding simple solutions is not doing things end-to-end. So I think we found a sweet spot on the trade-off between being end-to-end and finding simpler and traditional solutions. So thank you very much. This was the last question. As I said, NVIDIA will send you a follow-up email with a PDF that contains my contact details in the last slide, which you will have a link to my LinkedIn profile there, and a link to my Medium profile, where you can find blog posts that I wrote, both about deep learning papers and about a topic that is very, very close to my heart, building the culture for AI teams. Because as I implied earlier, I think that one of the things that will give the best value and make the team strongest is not necessarily only the technology, but the culture of the team, and being able to build a team that also can deliver very, very precise engineering and focus on simple solutions, which are two things that don't come naturally to many deep learning PhDs from my experience. And I think that, so you can find it in the last slide in the PDF that NVIDIA will send you, or you can Google my name and find my LinkedIn and add me there and send me any question that you have. My name is Idan Bassuk, and I really enjoy talking to you. You've been a great audience, and see you next time.
Thank you, Idan. An on-demand version of the podcast will be available shortly. Hope everyone has a wonderful day.